Hello everyone. Today I'm going to do a little repair video. I have here a Whistler 1600 watt power inverter. There seems to be some individual going around the internet posting glowing reviews of Whistler products, and I highly suspect that this individual either is an employee of Whistler or is paid by Whistler to post these reviews. And it's highly suspect that there's anything whatsoever special about these. But I was pretty curious, so I wanted to acquire one and take a look at it. However, I did not want to pay for one. So what I did instead is what I usually do. I found a broken one, and I'm going to attempt to fix this. And once it's repaired, then I can see how it compares to other inverters on the market. Now, some of these are repairable, some of them are not. Of course, anything is repairable if you want to spend the time and money on it, but for practical purposes, not all of these are repairable. If it's some sort of proprietary circuitry that doesn't work, you'd either have to buy another product to get that proprietary circuitry, which of course means you might as well just buy the inverter and throw this one away, or you'd have to recreate the circuitry yourself, which definitely isn't worth your time. So other times it's something extremely simple. I have no idea on this one. I just took it out of the box, and we're going to take a look at it. This is what the product looks like. There's really nothing too special about it. The only real interesting thing here, to me, is that they chose to put this stupid plastic piece over it that serves no purpose whatsoever except making it look like some sort of Xbox knockoff. All it does is insulate it so that it'll run hotter. And it makes you pay more, of course, because this is not free to make. So anyway, right off the bat, I'm pretty skeptical. Anyway, step one. There's a lot of things that could be wrong with this particular product, but I'll show you what I do very first thing. A very common failure mode for inverters in general is when somebody applies a voltage to the output. Say they try to backfeed into their house circuit and forget to shut off their main breakers or something, then it blows up the output stage. That's really common. Or you plug it into some sort of heavy inductive load like an electric motor, and it backfeeds when you shut it off and blows it up, something like that. So there's a really easy way to check that. You just take your multimeter with the inverter off, of course, set it to ohms, and plug it into the AC receptacle, one on each side. And this one's showing 23 mega ohms, which is good. So there's no problem there. It would be shorted or only a few ohms if it was bad. So I'm going to try measuring from each of these to ground. 12 kilo ohms, that's fine. This one to ground, 3 mega ohms. So none of these are shorted together. Now on some better inverters, this one's clearly not, I verified that already. On some better inverters, the neutral will be internally bonded to ground. And that's a sign of a better inverter. It's able to be hooked up to a hardwire configuration, say your house. This one they've done the cheap way, and it does not support that. That's not necessarily a problem, it's just a less expensive inverter. So there's no problem there. The next step could be to turn the inverter on, try to hook it up through a fuse or some sort of current limiting device, maybe a variable power supply that has a current limit on it. And that could certainly be the next step. But instead, because I'm curious anyway, and I'm going to open it up and look at it anyway, next I'm just going to open it up and take a look at what's inside. On a lot of inverters you can just remove this stamped steel bottom plate and it separates from the extruded aluminum part. But in this case I can't do that because this plastic piece mounts to the top and wraps around the feet. So I'll just remove the 4 Phillips screws here and the 4 Phillips screws on top and remove the plastic piece. Then it looks like there are these 4 standard Phillips screws right here that I'll remove. And hopefully we can get a look inside then. Sometimes they use security bits for this, but this one just uses Phillips. Just a general note, when you're working on anything, I like to take all the little small parts and throw them in a container so that I can find them later. Obviously something like this, if I just drop it on this black fabric, you'd probably never find it again. And it's really easy to lose little pieces like this, and there can be a lot of odd little pieces in a product like this, so I just use this little container here and throw them in there. You can use whatever. And this is what it looks like with the plastic part and the bottom removed. It looks like this inverter is constructed a little more complicated than necessary. It has this circuit board here that you can see, that does the conversion from 12 volts DC to 145 volts DC approximately. And then inside, which you can't really see yet, but inside there's another board down there, and that one does the conversion from high voltage DC to AC output. This board here, the components in there heatsink to some aluminum heat sinks on the other side that you'll probably see once I disassemble it. The board underneath heatsinks to this extruded aluminum case, the top of it specifically. And it's kind of funny. I suspect that engineering returned this product here, and marketing said, no, 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 that won't do. We want it to look like this. So they just added this plastic piece covering up the heatsink so that it doesn't do its job anymore and no longer performs as well. If you have one of these, just remove this stupid thing. It'll work better. Anyway, I'll flip this over again. And I also think it's kind of funny that if I don't know where it goes out of focus on you, but this is the ground input, and it flows through this portion of circuit board here. And you'll notice that the circuit board isn't adequate to carry that much current. So instead of actually fixing it, they just put this piece of wire in here and had somebody hand solder this in a fourth world country to handle the current. And there's not even adequate solder on the rest of it. It's kind of sad, actually. But I reserve judgment until we get a little bit further into it. Oh yeah, one more note. This was assembled improperly. You may not be able to see it on camera, but each of these screws here, where it attaches the heatsink to the circuit board, they over-tightened these and crushed the printed circuit board, which may or may not have done any damage, but it was not assembled properly. Anyway, I'm going to remove these 6 screws on the outside, which will allow me to remove this board, hopefully, from the housing so we can take a look at the other side. And also I'll have to remove a bunch of screws in the end panels so that I can slide those off to get these lugs out. But before I do that, I do want to do one thing just because it's convenient right now, and for that I'm going to zoom in here a little bit for you. I have my multimeter set to ohms, and on this circuit board here there is a row of transistors over here and a row of transistors over here. Looks like they're TO220s, 3-pin devices. So right here there's 3 pins sticking out. One is a drain, one is a source, and one is a gate. The gate has this little surface mount resistor going to it, and there are 1, 2, 3, 4, 5, 6 on this side and 6 on the other side. Another common failure is when these transistors overheat or have some other failure condition. Perhaps it was designed poorly and they overvolt in certain conditions, just a transient overvoltage that blows them up. Perhaps somebody connected it to a 24 volt battery instead of 12, who knows. But in any case, an easy way to tell whether these are good or bad, it doesn't guarantee that they're good, but an easy way to tell if they're bad, if they overheated and melted themselves together, which is what they usually do, and then they blow a fuse, is to test whether there is a connection between the gate and these other 2 pins. And there should not be a connection there. They should be high impedance. So I'm just going to take my multimeter, which I have set to ohms, and make sure that none of these 3 pins of the transistor are shorted together. Sometimes one of these will burn off, leaving just the other 2 connected, but I'm just going to go down all 6 of these and all 6 of these and make sure that those transistors are high impedance while the inverter is off and disconnected and discharged. Well, I have it pretty much disassembled, and I don't notice anything obviously wrong with it, except that it seems poorly designed, poorly engineered and poorly assembled. I'm not at all impressed with it. This is not an economical way to make an inverter, and they undoubtedly had to cut some corners because of that. I did look at the fuses, and the fuses are 6 35 amp fuses for 210 amps, I think, total, which is reasonable for a 1600 watt inverter. The electronics inside don't look like they're really good for anything all that much more than around 2000 watts, but again, maybe that's alright for a 1600 watt inverter as this is rated. We'll see how it performs if I ever get this thing running. But I did notice that one of the fuses looked kind of funny, and this is that fuse, and I'm not sure how well that shows up on camera, but there's actually, whoops, there's actually a blob of solder between the two terminals of this fuse, right in that fusible loop. So this fuse is completely disabled. It's just a dead short, no matter how much current you try to put through it. They power the FETs over here, a bank of 4 FETs, and those appear fine. They at least didn't let their magic smoke out yet, so I'm just going to put this fuse back in its holder and forget about it for now. But there's one quality defect right there. If we look at this board under here, it's pretty obvious that that one resistor, that greenish one that is now blackish, got way too hot. I don't think the resistor is actually damaged, it's just poorly designed, and it really can't handle that much heat. We'll see about that though. And then also right here on that IC, again, maybe you can't see it on camera, but there's a part kludged on with solder blobs. Obviously an afterthought there too. Anyway, I did remove this particular heatsink here just to get it out of the way. It's really complicated in its design, and that's just unnecessary. For example, inside this cup here, there's no fewer than 6 different kinds of screws. Why would you have 6 different kinds of fasteners for a product like this? There should only be 2. And most of the good inverters have only a couple different types of fasteners. They're designed that way, so that they're very easy to assemble. And this one, they don't care how easy it is to assemble, I suspect, because they farm it out to some country where you get paid 6 cents an hour, and it doesn't really matter. But anyway, that's enough of that. So my next step here is going to be down on this output stage board. You can see that there are, well, maybe you can't, but there's a bank of transistors, well, multiple banks on each side here. It looks like, I guess I'd have to take this board off to say for sure, so I won't comment. But there's multiple transistors on here. They look like, I guess I won't comment on that either. They're a slightly larger transistor, most likely the standard size they use in these, although they appear a little smaller. Anyway, I'm going to do the same thing I did on these that I did up here, and make sure that none of these are shorted together. The 3 pins, gate, drain, and source. And I'll let you know what happened there. On this board up here, I checked them all and they all seem fine. And here I can kind of sight down and take a look in there and make sure that there's no black spots anywhere, and they look fine there too. So I haven't really found a smoking gun yet in this inverter. I'm going to take a look at these transistors with my multimeter while it's powered off again, and I'll let you know what happens there. Now it's difficult to actually get the camera in here, so I'm just going to try to do it this way. Hopefully that's good enough. There appears to be some funny stuff going on over here on this side. There's actually 4 banks of transistors in here, but how they're arranged I'm not entirely sure yet, and it's pretty irrelevant at this point. One thing to note when you're measuring the resistance of transistors is that your test leads do put a voltage out when you're measuring ohms, and that voltage is high enough to turn on transistors. FETs have, if you put a voltage between the gate and the other pins on a FET, they can temporarily turn on, and that can last for several seconds. So if you're testing the gate of these and then you move to the drain or source, it may temporarily show a short before it goes away. So I typically check between the drain and source of the transistors first, make sure none of those are shorted, and then I go to the gates. Otherwise it can give you false readings. But just as an example here, if I go between the gate or the drain and source of this transistor, if I can do this here, it's showing almost a short, about 6 ohms, and that's not normal. If I go over to this side, these appear to be good. Go between the gate, if I can do this, kind of awkward with the camera in the way, go between the drain and source of this one, it's showing greater than 400 ohms. I have this set to 400 ohms, so it shows an open circuit, but that means it's greater than 400 ohms. So this side, a lot of the transistors are that way. This side, they seem to be fine. So the next thing I'm going to have to do is remove this board from the top. which is a real pain with all this junk here on these little short cables, but I'll get that done and then I'll turn the camera on again. And what do you know? This board inside is held in by yet another unique kind of screw. Lots of fasteners in this one. This is the bottom of that same board. There's one bank of transistors here, one here, one here, one here, one here, and one here. And over here, this is the top. The transistors over here, they all heat sink to the top right along these strips. These insulator strips, which are they're not really adhesive, but they're connected to this top plate of the inverter with some thermal compound, just standard white silicone-based thermal compound. And I noticed right away that there are none between the FET and this. This particular pad is not the compliant type, the silicone infused type that you can use as a pad without thermal compound in between. So when they assembled this, they either chose to cheap out and not put it there, or they outright forgot to. And I suspect they forgot to, because when I go over to this board, I can see that these transistors here are bad, and the rest of them look like they're good, just with my multimeter over here, which isn't a sure check, but it's a pretty darn good one. So now you can see a little bit easier what's going on the high voltage circuitry part of the board. I'm not going to talk about the low voltage part, the 12 volts DC to 100 and some volts DC, simply because that part probably works just fine. The problem seems to be on this board here, and I'm going to show you what that problem is. But first, this here is the high voltage side of it, so everything that's connected to this bus is 120 to 160 volts DC, something like that. It's unpowered right now, and this one here is ground. So this is your high voltage DC in, this is your ground, and the outputs are here. These 2 points right here, and these go to your outlet. And as is typical in a live neutral type inverter, the cheap kind, they have 4 banks of transistors. Normally they just use one or two larger transistors for that, but in this case they chose to use TO220s. So they have 4 here, these are all connected in parallel. They have 4 here, 4 here, and 4 over here. So there's really only 4 transistors on this board. They just chose to do it this way and put 4 in parallel instead of using larger ones. And that's just fine. I prefer the larger ones because there's fewer connections to solder. But once again, because they did this in some fourth world country, they didn't care. So they just used smaller FETs and probably saved a couple cents on their components that way, and didn't really have to spend anything on labor. So let's see if I can demonstrate for you what's wrong with this particular one. Now I have this set to ohms, auto-ranging ohms, and I'm just going to go between the drain and the source of some of these transistors. Drain is always in the middle, source will be in the opposite end of the gate, and again the gate is going to be connected to that small resistor. So here we have ground, and this is your output node going to your AC outlet. So I'll just ohm between these. And you can see that it's a relatively high impedance. This multimeter keeps auto-ranging, and it's just going to continue to auto-range. Now these are all in parallel, so they're all going to read the same value on this bank. And if I ohm between my gate and the drain, I also get a relatively high impedance. Now this bank over here seems to be the bank that has a problem. These are, I should mention, these are likely N-channel transistors, enhancement mode N-channel transistors, TO220 package, and usually they use 200 volt transistors for this in these inverters. 200 volts is probably why they blow up. They really should be using 250 volt or higher, but once again every penny they save counts directly toward their bottom line, so they don't care. Anyway, on this one I'll also probe between my drain and source, and you'll see here that they are basically shorted together. There's only a few ohms of impedance between them. And once again, I can go to any one of these in this bank, and they're all going to read the same because they're in parallel. Now, this entire bank is in parallel, so you can't ohm out to see which one is bad. And in this case, usually they're pretty well blown up and you can tell, but in this case you can't really tell which one of these four is bad just by looking at them. But there is a way that we can determine that, and once again I can just use this multimeter. No special tools required. I can ohm out between my gate and the drain because the gate to source voltage turns it on. And here I have about 100 ohms on this one. I'll go to this one over here. About 100 ohms, and that's reasonable when you have one of the transistors shorted. Go to this one. 100 ohms. Try this one. And it is a short. So, using very simple logic, one of these is not like the others. This transistor is bad. These other three are probably okay yet. So this is probably the only problem with this inverter. If I replace it, it most likely will work just fine. However, because these are all in a bank, I will likely replace all four of these at the same time. And this is just a different view of the same transistors. It's these four here that we're testing bad, and this one in particular. So I'm just going to bend this one up so we can get a look at it and see what it looks like. It doesn't look like there's anything wrong with it. So it's a good thing that we were able to just test with a multimeter to see what was wrong. And I'm curious on the brand here. I do not recognize this brand, nor any of the markings on it. So I cannot tell what this is or cross-reference it to determine what to replace it with. If anybody is watching and knows what that brand marking is, you can let me know. I'd be curious to know. I'm familiar with a lot of them, just not this one. You can also see that I tore up the printed circuit board a little bit. That actually doesn't matter in this case, but you do have to be wary of that. Normally I don't just bend them up like this, but I'm doing this just to demonstrate on camera. Anyway, especially since I don't know what that is, I'm going to go through and just replace this entire bank of 4 transistors. So let me go to my stash and see what I have that will work for this. Well, I did actually find out what that symbol on this transistor is. Dr. Google helped me out a little bit, and it's some unknown Chinese company that doesn't even seem to have English translations, so that's not a good sign. But it is a standard N-channel transistor, 200 volts, like I thought. And I'm going to use these. They're an on-semi product that is now obsolete, and has been obsolete for quite some time, so you can't get these anymore. But you can suspect how I got them. They're being thrown out, so I grabbed them. Anyway, I'm going to replace it with those. The ones that are on this board are very, very, very inexpensive parts. These are nothing special, but they are significantly better, which isn't always a good thing because there's going to be an imbalance now, potentially, in our AC waveform, but I'm not going to worry about that too much. And I do have 250 volt transistors, but there's no point in using those because all the rest of them on here is still 200 volts. Anyway, not sure if I'm going to record the soldering process or not, but I bet you're going to find out in the next few seconds. Well, I guess I am going to record it. So there's a lot of ways to remove these components. You can do whatever you want, but if you're not planning on reusing them, probably the easiest thing to do is to just cut it. Then you don't have to worry about removing all 3 pins at once. You can do them one at a time. This is a really cheap side cutter, but it'll work for this. And now the pins that are left over, this is a single-sided board, so I have to do all of my soldering from this side. I can just push through the board and remove one at a time. And they should now be visible on this side. And I'll just pull them out. There's one. 2, and 3. So the transistor is now removed, and before I can put the next one in, I need to refine that hole. Usually it's as easy as that. And this is the transistor that I'm going to be putting in there. I've decided, maybe out of laziness, but to just replace this one transistor. The rest of them seem to test just fine. I should probably back up. The next thing you're going to want to do is to take your transistor that you removed out of circuit and retest it with your multimeter. Make sure you remove the correct one. I did. And then recheck your circuit. Use the 3 transistors left in that bank and make sure that they perform as expected, or in this case, the same as all the others. And they do perform exactly the same as all of the others, so there's probably really no reason to replace those. It's still a good idea, but I'm just not going to do it. And should just be able to slip this one right in there, bend it over, and solder it in. There's not a whole lot to see, but you can just solder it right back in. Make sure that the solder flows up the lead a little bit. A lot of these boards are barely adequate to carry the current that's necessary. In this case, there isn't a whole lot of current there, so it doesn't matter much. But solder it in and make sure there's no shorts. I'm going to check that up closer after I turn the camera off. And that's about it. But I did want to mention quick that if you're doing work like this, I highly recommend a solder station. It doesn't have to be this brand, just some sort of solder station with a temperature regulated tip. You'll see why if you ever try to do this with a non-temperature regulated one. It works very poorly. They're not that expensive, so I would recommend it. If you're just doing this once or twice, then yeah, you can probably get by with the others. And I'm using this roll of solder. Again, you can use whatever brand you want. I recommend 63% tin, 37% lead. And yes, please do use leaded solder. Don't use lead-free solder. It works very poorly, higher temperatures, just all around bad. Use leaded solder. You can buy 6040 or 6337. 6337 is eutectic, so I'd recommend that. You can also get silver bearing solder, which is a little bit better for various things. I won't go into the technicals, but I find that it's completely unnecessary. Even though this is exactly the type of board where that would be beneficial, it really is pretty irrelevant. So this will work just fine, but 6337, that's what I'd recommend.